of days. Okay, number 10. Elastic spring has an unstressed length of 30 centimeters. So again, of course, I'm going to underline that, one of the key details. A load of 6 Newton is hung from the spring, and the length of the spring is now 66 centimeters. The 6 Newton load is removed and the spring returns to its original length. And then a load of 2 Newton is hung from the spring. They're saying, what is the new length of the spring? Now, you might be thinking that you want to use F is equal to Kx. And because you know the extension, what's the extension? Is 36. It goes from 30 to 66. You also know the load, so you could find out the spring constant and then use this equation again for the actual part where the load is 2 and you find out the extension. But there's a much quicker way to do it. And that's how we're going to do it. What is that? We know that extension is directly proportional to the force. What does that mean? It means that whatever factor the force increases by, the extension will increase by the same factor. In other words, if the force gets multiplied by 2, extension will also get multiplied by 2. If the force gets divided by 2, extension will also get divided by 2. So let's just compare the two cases. When we have a 6 Newton force acting, what's our extension? 66 minus 30. It's 36 centimeters. What's the new case? The load is now 2 Newtons. We want to know what's the extension when a 2 Newton load acts on the spring. Well, all we need to use is the idea of proportionality. When you go from 6 to 2, what is the factor? Meaning, what number are you multiplying or dividing with? You're dividing 6 by 3. What does that mean? That the extension will also get divided by 3. And that's your answer. So 36 divided by 3 is 12. That means the extension is now going to be 12. So what's the new length? The new length is going to be the original length plus the extension. And that's 42. We don't need to use the equation. So this is a really good question to actually see how proportionality works. Just to quickly show you, let's suppose if they had asked us, what's the new length if we replace the load with a 3 Newton load? In that case, going from 6 to 3, what are you dividing with? You're dividing it by 2. So the extension would also get divided by 2. In that case, the extension would be 18 centimeters, and the new length would then be 30 plus 18, which is 48. Number 11, it says, in which diagram does the height h represent atmospheric pressure? Pretty straightforward question, and we just have to see what's the height we're going to go with. It's definitely D. Why is it D? Because you start from the surface of the liquid, you go up to the height where at the point where the liquid ends, and above it, you must have a vacuum. So in this case, you just need to be sure that you don't mix the two, C and D, because in this case, you have air. And I'll just quickly tell you why can you not have air inside is because when you have air particles inside, they are going to exert a pressure on the liquid and they're going to push it down. So that is going to give you the wrong reading. That's exactly why it's important to have a vacuum above the column of liquid. We don't need to worry about 12, they've adjusted the syllabus, so we'll come to 13. Which one provides a continuous steady energy output for the longest time? Now again, when you're doing this on exam day, you better underline this: continuous, steady, actually saying the same thing, the longest time, so that you know this is exactly what you are shooting for. So we know that solar goes out, wind goes out. Why? Because it's variable, depending on how much solar energy there is or how much light there is, and then wind, obviously, depending on the wind. So we're left with 2 of these. So these ones are out. Both of these will give you steady supply, but clearly the 1.5 volt cell is going to run out after some time, right? So it cannot be the longest time. The nuclear reactor is going to be the right one. So number 14, it says a load is pulled by a rope attached to a motor, and the resultant force exerted by the rope on the load is shown in these diagrams. In each diagram, the load moves in the direction of the force shown and takes 10 seconds to travel 1 meter. In which diagram does the motor work with the greatest power? Now, quickly, we'll just write down the equation. For power, in this case, is going to be work done divided by the time taken. In case any of you is wondering as to why we're not using energy over time taken in this case, the answer is very simple, because they're clearly talking about work done. So it's the relevant thing to write here instead of writing energy. The other thing you should note is that all of them take 10 seconds to travel 1 meter. The time is the same for all 4 cases, which means that the denominator is not playing a role in this question. It's all about this. Wherever the work done is the greatest, that is also going to have the greatest power in this case. Why? Because the denominator everywhere is simply going to be 10 seconds. So all you need to see is where is the work done the greatest. Here, 12 times 1 is 12 joules. This one is 8. This one is 10. And this one is 4. So A has the most amount of work done, and that is going to have the most amount of power as well. Why? Because it's work being done in the same amount of time. So the amount of time is a constant in all 4 choices. What that means is that we don't have to do the whole working again and again. Because if you were to use the equation, I'll just show it to you for one case. For option A, you do 12 divided by 10, and you'd get 1.2, right? But then you divide this by 10, you divide this by 10, and you divide this by 10. So you're going to end up with the same result. So we don't need to do that. So number 15, electrical energy supplied is 600 joules, kilojoules actually. Of this energy, 45 kilojoules is transferred to the surroundings, and 15 is used to heat the casing of the kettle. The remaining energy is used to heat the water. They're saying, what's the efficiency? Now, be careful. In this case, they're not giving you the efficiency in percent form. It's just decimals. That means is that you simply need to work with the fraction. What's a fraction? It's the energy output divided by the energy input. That's it. You don't have to multiply with 100. So be careful. If you multiply with 100, you'd get it as, let's say, 70%. Then you know it doesn't match. And then you'd have to convert back to decimal. There's no need to multiply here. So what's the output? Well, input we know is 600. That's what we're supplying. But then 45 is going to the surroundings, and 15 is going to heat the casing. So that is not converting into output. What's the output? It is whatever energy is being used to heat the water. So the output in this case is 600 minus 60. And what's the input? That's 600. You get 540 divided by 600. So the efficiency is 0.9. And what does that mean? It basically means that 90% of the energy that we are supplying is getting converted into the output, which is heating up the water. And that's exactly the purpose here. So how is heat transferred through the vacuum of space? In this case, you must underline vacuum, again, to make sure that you don't forget the fact that we're dealing with vacuum in this question. We know that the only one that works is radiation. Why? Because conduction and convection, those two require a material medium for propagation. What does that mean? That they cannot travel from one place to another unless there is a material or there's a medium through which they can propagate or move. Radiation is the only one that is the exception. 17th, we have a cube and a thermometer. So what does it say? That each vertical face of the cube is painted a different color or has a different texture. Identical thermometers are placed at equal distances from each vertical face. So near which face does a thermometer read the greatest temperature? Now, what you need to do mentally in terms of processing this question is that you understand that, okay, how does a thermometer take a reading? Well, all of these faces, they will radiate heat, and the thermometer will absorb that heat, right? So whatever it absorbs is the reading that it's going to show. So then naturally, the next question you ask yourself, okay, which of these phases will radiate at the fastest rate? So we know that dull black surfaces are the best emitters and the best radiators of heat. Again, this is a common point of confusion. Dull black is not just a good absorber, it is also a good emitter. So both of those go hand in hand. For example, shiny white is not a good absorber. Similarly, if it's not a good absorber, it's not going to be a good emitter as well. So both of those go hand in hand. That's another important thing to remember. Now, again, why am I discussing these things with all of these questions? Is because the point is to quickly recall all of the things you've learned and see how they fit into the bigger picture, so that if you get a question that looks a little different, at least you're in a good position to apply what you know. This one again, the syllabus update, we'll ignore those and we'll come to question number 20. So steam condenses steam at 110 degrees C condenses on a surface to form water droplets at 100 degrees C. So there are two things taking place here. You have steam at 110 degrees C, and then it converts to water droplets at 100 degrees C. They're saying what happens after the steam comes into contact with the surface. So when it comes into contact, meaning as soon as it touches the surface. So we're not really worried about this process right here, right now. So when it comes into contact, the molecules are going to release energy. They will emit energy because the steam is cooling down. If they're releasing energy, what does that mean? That they have less kinetic energy left. Then if they have less kinetic energy, what does that tell you? That the molecules slow down. So this is the correct choice. If they had asked you about this part, what's happening when the steam is converting to droplets at 100 degrees C, you need to remember that whenever a change of state takes place, there is no change in temperature. The change in temperature is just zero. Why? Because that energy change or energy exchange that is involved is going in changing the structure of the substance from a gas to a liquid. So there are new bonds that are being formed, and that's why the energy has been released. The temperature does not change for any change in state, whether solid, liquid, gas, doesn't matter. All right, 21. Which list shows the states of matter in order of expansion from smallest to greatest for the same temperature rise? Once again, you underline these things. Now you see the point and benefit of underlining is that, sorry, give me a minute. So the point of underlining is so that we know, okay, this is exactly what we're supposed to pay attention to. You don't need to read the question again and again. So smallest to greatest expansion and same change in temperature. Well, in this case, we know that it's going to go from solid, liquid, gas. Where do we get the least amount of expansion is in the case of a solid. Then the liquid expands slightly more, the gas expands the most. Now again, what's the reason? Well, the reason is that the intermolecular forces, the bonds in a solid are very strong. So the energy input that goes into a solid is not enough to cause an increase in spacing. So there's a very small change. When you look at a gas, we know that the particles are very far apart. The fact that they're far apart means that the forces holding them together are much weaker. So when there's an energy input into a gas, it has a lot of impact. So it has a lot of effect. So that relatively they will move much more as they expand. And it's not the particles that expand, it's just that the distancing or the distances between the particles is increasing.